Hello, and welcome to another session on data mining. Today, we're going to step back a little and think at a higher level about vectors, matrices, dot products, projections, and some very basic concepts. And this is, of course, in line with with our module because we use these to move towards more deeper concepts in machine learning and data mining. So let's start with vectors. We've been talking about vectors for a while now, but if you think about it, we use numbers to measure stuff, right? Like, what's my height, for example? If you want to measure that, that can be expressed as a number, whatever. Let's say 5 feet, for example. So we've got a number and a unit, right? And that tells us the value of that quantity, and we have a certain unit, and that is what we can express using scalars, right? We can measure single quantities using scalars. Let's say if you got a height of a person, that can be expressed like this. This can be some quantities can be positive, some quantities can be both positive and negative, and of course there is that beautiful zero that is a very interesting number, I would say. So scalars are essentially quantities that measure uh, sig- using which we can measure single quantities, and we have operations like defined over them. We can add them. 5 feet plus 10 feet is equal to 15 feet, for example. And we've got other types of division and multiplication and subtraction, all those type of operations defined on these scalars. However, what to do when we want to represent multiple quantities associated with an object or a concept? So if you take the concept of a person, then you may want to express a number of attributes of that particular person, and those are all associated with one another. And we can do that using vectors. So we can have the height of a person and the weight of a person, let's say 100 kilograms or something like that, right? So that makes an abstraction or of the concept that we are trying to represent. So a vector is essentially an abstraction of multiple quantities typically associated with the same concept or with the same object. But we can also use vectors to indicate directions. And for example, we can have a vector called 0, 1, or which indicates, for example, this vertical direction, let's say north. So we can say that the north vector is 0, 1, and we can similarly have a south vector, which would be 0, -1, right? And so on, right? We can represent these we can represent directions using vectors as well. So some people say that a vector is a is an alphabet like this one with a small arrow drawn over it that represents that has a magnitude and a direction, right? So that's pretty much what we've been taught in high school, and it's nothing new essentially. But there's a small concept that I would like to emphasize here. It's moving from a single quantity to multiple quantities. That that's what we achieve when we move from scalars to vectors. Of course, we can represent multiple quantities, say using imaginary numbers. Like, let's say we can represent the north as 0 I unit vector plus j unit vector, but we can or we can represent it like 0 plus 1 iota, for example. But this is a bit more cumbersome in comparison to writing it like this. So it not only does it give us vectors, not only do they give us an ability to represent data more compactly, but they also give us an ability to do operations on top of that more in a more concise manner in comparison to say when we want to use or when we want to use these uh, complex numbers, right? So we can represent these vectors, and that's why they're really interesting. Of course, we can have a magnitude of a vector, which is nothing. We know or already know that it's going to be the first value squared, the second value squared, and the third value squared, and under the root, which essentially measures the distance of the vector from origin, right? So if this is a vector, then we can calculate its length or the magnitude of it using this distance function. And that is where the concept of distance enters into vectors. So if you're representing a point as a vector, you can calculate the distance between 2 points by using a distance formula, right? So if you have the Euclidean distance between 2 points, this is what we get. We can have other types of distances as well. So for example, there's something called, so this is Euclidean distance. It's also called the two norm distance, or some people call it L2 distance. And then we can have one norm distance as well. Let's say we can have u1 minus v1 absolute plus u2 minus v2. If you have these two vectors, and this is called the Manhattan or L1 distance between 2 points. Okay, so you can have that calculated between two different points, right? So the length of a vector is essentially the distance of the vector from the origin, which we already talked about earlier. And we've also talked about dot products, right? So we have a dot product, which is essentially measures how much along one vector is along another, right? So if you've got two vectors, you can take their dot product, which is essentially a sum of products. So you take the first element of the first vector, multiply it with the first element of the second one, and you take the second element of the first vector, multiply it with the second one, and then you add them together, right? So this quantity over here is a scalar quantity emerging out of the product of, or the dot product of two vectors. And it essentially measures how much uh, one vector is along another vector. And I'm going to show you pictorially, this thing pictorially in just a minute. So let's say if you got two vectors and we want to calculate, we calculate the distance between them, then we can expand it as follows. Let's say we've got two-dimensional vectors, u and v. We take the norm of these and we square it. So we're using the square of the norm as the distance. Then we have u1 minus v1 squared plus u2 minus v2 squared. And we can expand it. But if you rearrange it and if you pay attention to the algebra, it's trivial once you get the hang of it. You can express it like this. You can express it in terms of the norm of u vector, which is can also be written as u transpose u. You can have v transpose v, and then you have another dot product. And then we've already talked about it a bit, and that is the relationship between distance and dot products, right? So everything is coming together nicely, right? In order to get a better understanding of what dot products actually is essentially measure projections. So let's say if you got a point, if you got two vectors, you got a vector w and you got a vector x, then what, if I take this point, this is the representation of the point w as a vector, and if I take 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 a light source and such that that is perpendicular, the light source is perpendicular to this vector x, then the shadow that this point is going to make on this vector x is going to be called the projection of this vector w onto x. And that is the length of this projection, which is going to be z. Okay. Similarly, you can have the projection of x on w vector, by this time shining light on that is perpendicular to w and looking at where it makes a shadow, and we can see that this length is also going to be equal to z. So if you think about dot products is nothing but the projection of one vector onto another vector, and it's commutative as well. You all know that, right? So that's really nice. The real thing that I want you to learn is to be able to essentially enjoy dot products. They're everywhere in machine learning. And as a computer scientist, we typically don't like mathematics very much, much less linear algebra. But it's really essential. If you want to develop novel machine learning methods, it's important to understand a bit of linear algebra because it allows us to express a certain problem much more compactly. That's one of the, so if you have a very complicated mathematical framework, mathematical equation, as I'm going to just show you in just a minute, you can express it very compactly using matrix vector dot matrices and vectors and so on, rather than using scalars only, right? The other thing is there are certain algorithms that run that if you vectorize the same problem, you get a significant speed up in on your machine, right? So let's say if you want to do the following computation, AB plus CD plus EF, right? And you express it in vector form, then there are specific libraries that are faster when the code is vectorized. So there are significant computational efficiency benefits of converting problems from mere scalar evaluations to vector ones. And this is at the core of deep learning because uh, if once you learn how to express a particular problem in terms of vectors and matrices, then what deep learning revolves around is a concept of tensors, and we're going to talk about those once we get there. But let's get started with something very basic. Let's say if you got a sum of products, and we know that a dot product is a sum of products as well, right? That means if I see a sum of products like this one, then that means I can express it as a dot product, right? So this is a sum of products. So sum of products, and we can express it as a dot product. Let's say if I make a vector and I lay the vector down rather than making it vertical like this one, so essentially taking a transpose of that vector, then I can write the vector ACE, and then I have another vector BDF, and let's say I call the first vector P, and I'm taking a transpose of it. That's why it's laying down. And then we have got a vector Q, which is BDF, and whatever this sum of product was going to come out, the same thing is going to come out of this, right? And that also means that we can express anywhere you see anything like this, where you have sum of square terms, that means that probably it can be represented as a vector norm as well. So let's say we got a vector that is ACE, and you have an expression a squared plus c squared plus e squared, then we can express it as this thing, as the squared norm of p vector. Okay, so love dot products and learn to spot them. And wherever you spot them, you should be able to write a more compact representation of a much larger expression, right? So that's the demonstration of that. And also, not only that, you should also be able to spot matrix vector products. Now, remember, vectors are when we want to express multiple quantities, but what if we want to express multiple vectors? Then we use matrices, right? Or what if I want to operate on a particular vector? Then we use matrices. So let's say if you've got a system of linear equations like this one. So we've got AB plus CD plus EF equals U, and then we've got another equation that is AG plus CH plus EK is equal to V. This sum of product form tells me that probably I can express this as a dot product, and we've got another dot product here. So we'll have two vectors, right? But if you look closely, then A, C, and E are being repeated in both of these equations, and that means we've all done this in high school or something. But what this means is that there's a single vector that is being multiplied by two other vectors, which I put in this matrix. And I can write this right-hand side as a vector as well. And then that means this whole thing can be expressed as this linear equation, which I can then write as let's say, a P is equal to, let's say in this case, let's call this UV vector V vector, right? So let's say we've got this vector, and typically matrices are indicated by capital. So this simple equation tells me that this is going on, right? So you should be able to love matrix vector product. This is a matrix product with a vector. So a matrix is being multiplied with a vector and gives rise to a vector. So you should learn to spot them. So that would make your life pretty easy by writing more compact representations of these things. Okay. So we're going to talk about these matrix vector products. One of the best things about matrix vector products is that they're really efficient computational libraries that can calculate these very fast. Okay, so whenever rather than doing or computing these things manually, or writing these expressions as scalar within your program, if you write it in terms of these matrix vector products, probably you're going to get a major speed up. That's the logic behind making languages such as MATLAB, in which essentially everything is a matrix, right? Moving on, if you want to operate on a vector, you can think of using matrices. So one way of thinking about matrices is that they are a collection of vectors. I've already shown you that, right? So we can represent the data set for a given problem as a data matrix, in which each row is represented as a representation of a single example or a single data point. But what we're more interested in is understanding how matrices can be viewed as operators on vectors. So let's say we've got a matrix over here. Okay, it's a matrix 2, 0, 0, 2, and then we've got a vector that is 0, 1. If I multiply this matrix with this vector, then I get, if you follow the simple rules of matrix vector products, then you get this multiplied with this gives rise to 0, which is the first element over here. And then we got the second element, which is 2. So you got a new vector. So when you multiply x with t, you get a new vector, which I'm calling y, and it's a different vector from x, right? Now, if you think about it, the effect of this matrix multiplication is the following: that this point 0, 1 has changed or has been transformed into a new point that is 0, 2. So if you view it geometrically, you've got a point over here, which is 0, 1. And once you multiply it with the matrix T, what happens is that you get a new point, which is 0, 2 now, right? That's interesting. So matrices essentially transform points. So matrix multiplication with a vector can be viewed as an operation on the vector or transformation on the vector. And you can verify this geometrically in your spare time. We're going to talk about a very specific type of vectors which are called, or which are associated with a given matrix, which are called eigenvectors. Now, some people are scared of the name of this thing, but if you think about it, it's nothing big. It's essentially, so if you're given a matrix, let's say if you're given a matrix like this one, 2002, it's exactly the same matrix that we talked about. And you have a vector called, let's say, 0, 1 in this case. And once I multiply this matrix with this vector, I get another vector, which is 0, 2. And if you look at it, the, the relationship between the original point, 0, 1, and the new point that we got after multiplication, which is 0, 2, there is a relationship between these two. Both of them are collinear. What that means is that both of these points lie on in the same direction. So although the point has changed, like the output y is different from the original point x, but both of them are in the same direction. Those those points, those vectors, which when multiplied by a matrix, a particular matrix, give rise to new points which are exactly in the same direction. There is no rotation involved. So either they are exactly in this direction, like in this one. So both of them have shared the same direction, right? They can be exactly opposite to each other, but what cannot happen is that so you understand, like you've got this point, and once we multiplied it, you got this point, and both of them have the same direction. If that is the case, then this uh, vector that we have will be called a characteristic vector of this matrix, or an eigenvector in German. Okay, that's where the word comes from. There's a fun way of remembering it. You can think of these as, I don't want to use the word nasty, but these are stubborn points that only undergo a change in direction, do not undergo a change in direction when they are multiplied by a particular matrix. So each matrix is going to have a set of characteristic or eigenpoints which are stubborn. Don't quote me, but just use this to remember that only undergo a change in direction when they are multiplied with the matrix. So 0, 1 in this case is going to be an eigenvector, okay, because once we multiply this matrix T, all the only thing we see is a scalar change in the direction. There is no scalar change, no change in direction. So if you multiply, the definition of the eigenvector is the following. If you V is going to be an eigenvector of given matrix T. If you multiply T with V, and you get a vector that can be expressed as a scalar vector product of the original vector. So let's apply this definition over here. So you had a point X, which is 0, 1, and we had a matrix T. So once you multiply these, y is equal to tx, you get another point, which is 0, 2, but that can be written as 2 times 0, 1 or 2 times x. So in this case, lambda is equal to 2. That means this x thing over here, this vector is an eigenvector of this given matrix. Okay. For your convenience and to help you understand this concept better, I've made a IPython notebook that you are welcome to explore on your own, and it essentially helps you understand how matrix vector products are transformations, and then what are eigenvectors for a given matrix. And it's in Python, so you should be able to do that. Let's take another example. Let's say if you got a matrix T is equal to 3, 0, and 1, 2, and then let's say we're given a vector 1, 0, then we can verify that this is actually an eigenvector by simply multiplying this point that is given to us with the original matrix. And we see that we get a vector which is 3, 0, which can be expressed as 3 times the original vector, 3 into 1, 0. So there is only scaling going on. There is no change of direction. Okay? So this vector then over here is an eigenvector of this matrix. Similarly, you can also verify that this vector is also an eigenvector of the original matrix. And you've covered this concept probably in high school, but some people find it a bit difficult. So I hope the geometrical relationship helps you understand this. So let's say if you got a vector over here and you multiply it with a matrix, and the only thing you see is a change in scale, so no change in direction is involved, then that point is an eigenvector or characteristic vector of that particular matrix. And the library that the notebook that I have over here would help you understand it further. Okay. So I hope you understand the concept of eigenvectors. Remember, whenever you have a matrix vector product leading to a scalar change in the vector, then V is going to be the eigenvector of T. So this is called the eigenvector problem, and we are going to use this in our downstream machine learning algorithms. Thank you.